and welcome best at Mathematics 3-1 in this course subject M112, the number theory. So in this video, Nette Arago, Maila Doroy, Aivril Arris Ongcog, Cherilyn Acog, Isabelle Lonod, Maxine Jandayan, and Nicel Salise will discuss three topics, which are the fundamental theorem of arithmetic, the Seive of Erathostenes, and the Goldbach Conjecture.
Fundamental theorem of arithmetic. An integer p greater than 1 is called a prime number, or simply a prime, if its only positive divisors are 1 and p. An integer greater than 1 that is not a prime is termed composite. So, among the first 10 positive integers, 2, 3, 5, and 7 are primes, and 4, 6, 8, 9, and 10 are composite numbers. Note that the integer 2 is the only even prime, and according to our definition, the integer 1 plays a special role, being neither prime or composite. For the theorem 3.1, if p is a prime and p divides the product of a and b, then p divides a or p divides b. So we have here the proof. If p divides a, then we need go no further. So let us assume that p does not divide a, since p and a are relatively prime. So because the only positive divisors of p are 1 and p itself, since we are dealing with the prime numbers, this implies that the GCD of p and a is equals to 1. So from the mere definition above of the theorem 3.1, we can cite in the Euclid's lemma that we get p divides b. So for the corollary of theorem 3.1, for the corollary 1, if p is a prime and p divides a sub 1, a sub 2 to a sub n, then p divides a sub k, where k is greater than or equal to 1 but is less than or equal to n. For corollary 2, if p, q sub 1, q sub 2 to q sub n are all primes, and p divides q sub 1, q sub 2 to q sub n, then p is equals to q sub k for some k, where k is greater than or equal to 1 but is less than or equal to n.
At this point, let us proceed to the theorem 3.2, or the fundamental theorem of arithmetic. So this theorem states that every positive integer n is greater than 1 is either a prime or a product of primes. So this representation is unique, apart from the order in which the factor occurs. So for the proof, either n is a prime or it is a composite. So in the former case, there is nothing more to prove. If n is composite, then there exists an integer d satisfying d over n, and d is greater than 1 but less than n. Among all such integers d, choose p sub 1 to be the smallest, and this must be a prime number. Otherwise, it too would have a divisor q, with q is greater than 1 but less than p sub 1. But all the q over p sub 1 and p sub 1 over n imply q over n, which contradicts the choice of p sub 1 as the smallest positive divisor, not equal to 1 of n. So let's have an example for this theorem. We have here the positive integer 360. So by prime factorization, we'll get the prime factors of 360. So 360, the factors are 10 and 36. So for 10, the factors of 10 are 2 and 5. So since 2 and 5 are already prime numbers, we'll stop here. So let's proceed to 36. So the factors of 36 are 6 times 6. So the factors of 6 are 2 and 3. So we already get the 5 factors of 360, since 2 and 3 are prime numbers. So we can express this as 360 is equals to 2 times 2 times 2 times 3 times 3 times 5. So by collecting the like primes and replacing them by a single factor, we can rephrase theorem 3.2 as a corollary. So the corollary states that any positive integer n is greater than 1 can be written uniquely in a canonical form. To illustrate, the canonical form of the integer 360 is 360 equals 2 to the power of 3, since we have 3 2's here, and so 2 to the power of 3 times 3 to the power of 2 times 5. So another example, we have 4,725 is equals to 3 to the power of 3 times 5 to the power of 2 times 7, and 7,460 is equal to 2 to the power of 3 times 3 to the power of 2 times 5 times 7 to the power of 2. So prime factorizations provides another means of calculating greatest common divisors. So by allowing zero exponents, we can write a is equals to p sub 1 to the raised to the power of k sub 2 times p sub 2 raised to the power of k sub 2 to p sub n to the power of k sub n. So for b, we have b equals p sub 1 raised to the power of j sub 1 times p to the power of p sub 2 raised to the power of j sub 2 to p sub n raised to the power of j sub n. So we have here GCD of a and b is equals to p sub 1 r sub 1 times p sub 2 raised to the power of r sub 2 to p sub n raised to the power of r sub n, where r sub 1 is the minimum of k sub 1 and j sub 1. So the smaller of the two exponents associated with p sub 1 two representations. So in the case of our previous example, we have, so we let a is equals to 4,725 and b is 17,460. So let us rewrite the factors. So we have here 4,725 is equals to 2 raised to the power of 0. So again, by allowing zero exponents, we have to write 2 here because it is present in b. So we have to make it balance. So again, 4,725 is equals to 2 raised to the power of 0 times 3 raised to the power of 3 times 5 squared times 7. And for 17,460, it is equals to 2 raised to the power of 3 times 3 to the power of 2 times 5 times 7 squared. And so for the GCD, again, we have to get the smaller of the two exponents associated with p sub 1. So the GCD of 4,725 and 17,460 is 2 raised to the power of 0 because 0 is smaller than 2 raised to the power of 0 is smaller than 2/3 times 3 squared times 5 times 7. So if we multiply it all, we will get the product 315. So the GCD of 4,725 and 17,460 is 315. So this is an opportune moment to insert a famous result of Pythagoras. So mathematics as a science began with Pythagoras, and much of the content of Euclid's elements is due to Pythagoras and his school. The Pythagoreans deserve a credit for being the first to classify numbers into odd and even, prime and composite. So to discuss the theorem 3.3 of the Pythagoras, let me give the floor to the next reporter.
Moving forward with Theorem 3.3, Pythagoras, where the number square root of 2 is irrational. Here's our proof. If we want to prove that the square root of 2 is irrational, then the negation is to assume that the square root of 2 is rational. Then, square root of 2 equals a over b, or square root of 2 could be expressed as a fraction where our a and b here are positive integers because our 2 is positive with GCD of ab equals 1. Our a and b here could not be equal to 0 and therefore must be greater than 0 because from what I've said a while ago that our value of a and b are positive integers with a GCD of a and b equals 1. Next is squaring both sides. We have square root of 2 squared, which is 2 equals a squared over b squared. the b squared in our denominator moves to the top on the left side. So we have accumulated the answer of square root of a squared equals 2b squared, so that b divides a squared, and therefore 2 will be a factor of a. Next, if our b is greater than 1, then the fundamental theorem of arithmetic guarantees the existence of a prime p such that p divides b. Recalling the fundamental theorem of arithmetic, in which an integer p is greater than 1 is called a prime number, or simply a prime, if its only positive divisors are 1 and p. And it follows that p divides a squared, and by theorem 3.1 that p divides a. And recalling the theorem 3.1 that if p is a prime and p divides ab, then p divides a or p divides b. So it was discussed a while ago. Hence, our GCD of AB is greater than or equal to P. We therefore arrive at a contradiction. Unless our B is equals to 1. Diba? But if this happens, then a squared equals 2, which is impossible. We assume that we are willing to grant that no integer can be multiplied by itself to give 2. Our supposition that square root of 2 is a rational number is unattainable, and so square root of 2 must be irrational. But here's another way. There is an interesting variation of proof on Theorem 3.3. Another possible way is to let square root of 2 be a rational number. We can find two integers a and b which is not equal to 0. So our a and b here is not equal to 0. Our value such that diba lahat naman ni ang kaning atong value na square root of 2 equals a over b with GCD a of ab equals 1. So there must exist integers r and s satisfying ar plus bs equals 1, as GCD of ab equals 1. To get here the value of a equals square root of 2b and square root of 2a equals 2b, we cross multiply the value of square root of 2 equals a over b, and that would be square root of 2a and square root of 2b. So notice here that our function here is from the square root of 2 is equals to, because we added integers r and s to satisfy ar plus bs, so square root of 2 times ar plus bs is equals to, we use the distributive property, and it equals to square root of 2a times r plus square root of 2b times s, and that will be equal to 2br plus as. Ano na 2br plus as na siya? Okay, diba? Ato ang cross multiply to ganina, and our value of our a times square root of 2a is equals to 2b, and our value of square root of 2b is equals to a, so that is 2br plus as. Our a corresponds to square root of 2b, and square root of 2a corresponds to 2b, and that will be our value. After that, we can write ato naman ni siya complete. Then the Then the representation of square root of 2 leads us to conclude that square root of 2 is an integer. An obvious impossibility, we conclude that square root of 2 is irrational. And that's Theorem 3.3, Pythagoras, proven that the number square root of 2 is irrational.
The Seive of Erathostenes. The Seive of Erathostenes is a method for finding all primes up to and possibly including a given natural n. So this method works well when n is relatively small, allowing us to determine whether any natural number less than or equal to n is prime or composite. So in testing the primarily of a specific integer, a greater than 1, it is therefore sufficient or to divide a by those primes that not exceeding square root of a. So presuming, of course, the availability of a list of primes up to square root of a. So this may be clarified by considering the integer a equals 509. In as much as 22 is less than the square root of 509 and less than 23, we need only try out the primes that are not larger than 22 as possible divisors. So, namely, ang musudra nga prime adto is from 2 to 19. So, dividing 509 by each of these in turn, we find that none serves a divisor of 509. So, those primes nga from 2 to 19, wala makadivide sa 509. So, to conclude, is 509 must be a prime number. So before going to fit provides a practical means for determining the canonical form of an integer. So say we have here 2093 or a equals 2093. So first ganina na nag-1 to sa square root, which is 45 is less than the square root of 2093 and less than 46. It is enough to examine the primes 2 to 43, the 2 primes na masud from 2 to 43. So by trial and error, the first of these to divide 2093 is 7. And then 2093 is just equals to 7 times 299. So as regards the integer 299, the 7 primes that are less than 18, note that na 17 is less than the square root of 299 and less than 18. So primes na pwede na ito na-divide is from 2 to 17. So 2, 3, 5, 7, 11, 13, or 17. So the first prime divisor of 299 is 13. And it is carrying out the required division na na-obtain na is 299 equals 13 times 23. But 23 itself is a prime. So makakonclude na na 2093 has 3 exactly prime factors, and those are 7, 13, and 23. So 2093 is just equals to the 7 times 13 times 23. So when you skip the Erathostenes without checking without knowing the background. So this is the background of Erathostenes. So he is a Greek mathematician whose work in number theory remains which is significant in Servile. So that is before Christ era 276 to 124. Although posterity remembers him mainly as a director of the world-famous library at Alexandria, Eratosthenes was gifted in all branches of learning. If not a first rank in any, in his own day, he was nicknamed Beta, because it was said he stood at least second in every field. So perhaps the most impressive feat or feature of Eratosthenes was the accurate measurement of the Earth's circumference by simply the application of Euclidean geometry. So we have seen that if an integer a greater than 1 is not divisible by any prime p less than or equal to the square root of a, then a is of necessity of a prime. Eratosthenes used this fact as the basis of a clever technique called the Seive of Erathostenes for finding all primes below a given integer n. So the scheme calls for writing down the integers from 2 to n in their natural order and then systematically eliminating all the composite numbers by striking out all multiples 2, p, 3p, 4p, 5p, or the primes p less than or equal to the square root of n. So the integers that are left on the list, those that do not fall through the sieve, are primes. So we have here an example. Consider all the integers from 2 to 100. So, yeah, list na to ang numbers from 2 to 100. So, mag-start sa 2 and then 100. So, first to do is to cancel out even numbers because even numbers are composite numbers. So, ang cancel na to ang 4, 6, 8, 10, and even numbers until the 100. So, ang mabili na lang is 2, 3, 5, 7, 11, 13, 17, 19, 31, and 23, and so on. Next thing to our next number to cancel is multiples of 3 because those are adds pero hindi siya prime. Kaya may siya multiples or ma-divide lang siya. So those are 9, 15, and 21. So naman natin cancel ang multiples of 3 at na po sa multiples of 5. Though, parang na-cancel naman nato ang 10 and 20 kay even man siya so automatically wala na. Those are multiples of 5. And then 15 also. And makancel sa siya kay multiples of 5 din sila. So now makadivide din niya which is 3 and 5. So 7, dili na ito makancel sa 7 because wala yung maka-divide niya either 2, 3, or 5. 2, 3, or 5. So, that just include the prime si 7 and 11 also. So, ang final na nabili na to is 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31 also, we have 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, and lastly ang 97. So those numbers na wala na tumakas out are all prime numbers na less than 100. So by this point, our obvious question must have occurred to ourselves na ba kahay largest prime number or do the primes go on forever? So ma-answer na siya sa Book of Elements Unit. Ito. Euclid's argument is universally regarded as a model of mathematical elegance. So, loosely speaking, it goes like this. Now, given any finite list of prime numbers, one can always find a prime not on the list. So, hence, the number of primes is infinite. And to prove this, of course, Nette theorems. And this is to be discussed after me.
For that theorem 3.4 in a Euclidean, so there is an infinite number of primes. So here is the proof, and the Euclid's proof is by contradiction. So we let p sub 1 is equals to 2, then p sub 2 is equals to 3, and p sub 3 is equals to 5, and p sub 4 is equals to 7. So be the primes in ascending order, and suppose that there is a last prime called p sub n. Now, consider the positive integer. So, we'll let p is equals to p sub 1, p sub 2 to p sub n plus 1. So, for a prime number p, define p raised to a number to be the product of all primes that are less than or equal to p. Numbers that form p raised to a number plus 1 might be termed Euclidean numbers. So because they appear in Euclid's scheme for proving the infinitude of primes, it is interesting to note that in forming those integers, the first 5 namely. So here is the first 5 integers, or forming those integers na consider natin as prime numbers. So, 2 raised to a number plus 1 is equals to 2 plus 1 is equals to 3. 3 raised to a number plus 1 is equals to 2 times 3 plus 1, which is equals to 7. Then for the third one is 5 raised to a number plus 1 is equals to 2 times 3 times 5 plus 1 is equals to 31. For the fourth number, we have 7 raised to a number plus 1 is equals to 2 times 3 times 5 times 7 plus 1 is equals to 211. And for the fifth number, forming those integers, we have 11 raised to a number plus 1 is equals to 2 times 3 times 5 times 7 times 11 plus 1, which is equals to 2,311. So those are all prime numbers. However, there are also existing numbers which we concluded as or not a prime numbers. So we have 13 raised to a number plus 1 is equals to 59 times 509. 17 raised to a number plus 1 is equals to 19 times 97 times 277. And last is 19 raised to a number plus 1 is equals to 347 times 27,953. So those are not prime. So at present, 22 primes of the form p raised to a number plus 1 have been identified. So the first few correspond to the value p is equals to 2, 3, 5, 7, 11, 31, 379, 1019, 1021, 2657, 3,229. So the 22nd occurs when p is equals to 392,113 and consists of 169,966 digits. So imagine how many digits it composed. So it was found in 2001. So here is the equation. First is n sub 1 is equals to 2, n sub 2 is equals to n sub 1 plus 1, n sub 3 is equals to n sub 1, n sub 2 plus 1, then n sub 4 is equals to n sub 1, n sub 2, n sub 3 plus 1. So if we will break it down, we have n sub k is equals to n sub 1, n sub 2 to n sub k minus 1 plus 1. So let P denote the nth of the prime numbers and their natural order. So Euclid's proof shows that the expression P sub 1, P sub 2 to P sub n plus 1 is divisible by at least one prime. So if there are several such prime divisors, then P sub n plus 1 cannot exceed the smallest of there, so that P sub n plus 1 is less than or equal to P sub 1, P sub 2 to P sub n plus 1 for n is greater than or equal to 1. Another way of saying the same thing is that P sub n is less than or equal to P sub 1, P sub 2 to P sub n minus 1 plus 1, where n is greater than or equal to 2. With a slight modification of Euclid's reasoning, this inequality can be improved to give P sub n is less than or equal to P sub 1, P sub 2 to P sub n minus 1, where n is greater than or equal to 3. For instance, when n is equal to 5, this tells us that 11 is equals to P sub 5 is less than or equal to 2 times 3 times 5 times 7 minus 1, which is equals to 209. So we can see that the estimate is rather extravagant. A sharper limitation on the size of P sub n is given by Ponce's inequality, which states that P sub n raised to the power of 2 is less than P sub 1, P sub 2 to P sub n minus 1, where n is greater than or equal to 5. This inequality yields P sub s raised to the power of 2 is less than 210, or P sub s is less than or equal to 14. A somewhat better size estimate for P sub s comes from the inequality of P sub 2 sub n is less than 2 P sub 2, P sub 3 to P sub n minus 2, where n is greater than or equal to 3. We obtain that P sub 6 is greater than P sub 5 but is less than 2 P sub 2, and P sub 3 minus 2 is equals to 2 times 5 minus 2, which is equals to 13. So to approximate the size of P sub n from these formulas, it is necessary to know the values of P sub 1, P sub 2 to P sub n minus 1.
Theorem 3.5. So if P sub n is the nth prime number, then P sub n is less than or equal to 2 raised to the power of 2n minus 1. So here's our proof. Let us proceed by induction on n, the asserted inequality being clearly true when n is equals to 1. And as the hypothesis of the induction, we assume that n is greater than 1 and that the result holds for all integers up to n, then we have P sub n plus 1 is less than or equal to P sub 1 plus P sub 1, P sub 2 until P sub n plus 1. And if we multiply 2 times 2 raised to the power of 2 until 2 raised to the power of 2n minus 1, then we have accumulated the 2 raised to the power of 1 plus 2 plus 2 raised to the power of 2 plus 2 raised to the power of n minus 1 plus 1. So we recall the identity that 1 plus 2 raised to the power of 2 plus 2 raised to the power of n minus 1 is equals to 2 raised to the power of n minus 1. And we obtain that P sub n plus 1 is less than or equal to 2 raised to the power of 2n minus 1 plus 1. However, 1 is less than or equal to 2 raised to the power of 2n minus 1 for all n, whence P sub n plus 1 is less than or equal to 2 raised to the power of 2n minus 1 plus 2 raised to the power of 2n minus 1. And multiplying 2 times 2 raised to the power of 2n minus 1 is equals to 2 raised to the power of 2n. So nakita na dira. So in this theorem, we are listing the prime numbers, and this theorem says that for any position in our list, diba, the prime number at that spot won't be too big. So dili kay dako mo ng aning 1. And specifically, it won't be larger than 2. So, dili mo dakuan ng 2 raised to the power of twice the position minus 1. It's a way of setting up an upper limit on how large prime numbers can be based on where they are in the list. And it is called the Bertrand's postulate or Chebyshev's theorem. So, it's interesting because we have this corollary to theorem 3.5, which is for n is greater than or equal to 1, there are at least n plus 1 primes less than 2 is raised to the power of 2n. So proof from the theorem, we know that p sub 1 times p sub 2 times p sub n plus 1 are all less than 2 raised to the power of 2n. So ato na na-discuss, no? Ang theorem 3.5 ito ganina. And in 1845, ato nang introduce si Joseph Bertrand conjecture that the prime numbers are well distributed in the sense that between n is greater than or equal to 2 and 2n there is at least one prime, and he was unable to establish his conjecture but verified it for all n is less than or equal to 3 million. So in this corollary, as we count higher in our list of numbers, there will always be at least as many prime numbers as the number we're counting up to, multiplied by 2 plus 1. So for example, if we're counting up to 5, there will be at least 5 plus 1 equals 6 prime numbers in that range. So let us content ourselves with saying that the first proof was carried out by the Russian mathematician P.L. Chebyshev in 1852, granting the result that it is not difficult to show that p sub n is less than 2 raised to the power of n and n is greater than or equal to 2. And as a direct consequence, p sub n plus 1 is less than 2p sub n, for n is greater than or equal to 2, and in particular, 11 is equals to p sub 5 is less than 2, and times p sub 4 is equals to 14. So, makita na to that we argue by induction on n, and clearly, p sub 2 is equals to 3 is less than 2 raised to the power of 2, so that the inequality is true here. Now, assume that the inequality holds for an integer n, whence p sub n is less than 2 raised to the power of n. And invoking the Bertrand's conjecture, diba? There exists a prime number p satisfying that p is greater than 2 raised to the power of n and less than 2 raised to the power of n plus 1, that is p sub n is less than p. So this immediately leads to the conclusion that p n sub n plus 1, p is greater than or equal to p sub n plus 1 and less than 2 raised to the power of n plus 1, which completes the induction and the proof. So maprove na to ang theorem 3.5. And primes of social form have been of perennial interest. Among these, the repugnant primes are outstanding in their simplicity. A repugnant is an integer written in decimal notation as string of 1, such as 11, 111, or 1111. So each integer must have the form of the quantity of 10 raised to the power of n minus 1 divided by 9. So we use the symbol r sub n to denote the repugnant consisting of the n consecutive ones. So now we can see the how many r with denoting the repugnant. And it is known that the only possible repugnant primes r sub n for all n is less than or equal to 49,000 under the 9 numbers just indicated. So no conjecture has been made as to the existence of any others. So it's saying that when we look at the next prime number after any prime number, the next prime is always less than double the current one. So it's a way of showing that prime numbers don't grow too fast compared to the numbers that come before them. So this explains the truthfulness of this theorem.
So, good day everyone, this is Maria Isabelle Lonod, and I will be the one to discuss to you the Goldbach Conjecture. So, Goldbach Conjecture, it is proposed by Christian Goldbach, who is a Russian mathematician, and he is very devoted in his work about prime numbers. Goldbach Conjecture, so it is an unanswered question whether there are infinitely many pairs of twin primes. He is very curious about this way before if were added up together Or is it just on one happening or one situation where when we add two prime numbers, is it equal to an even number? So with that, he discovered this theory. It is an unanswered question whether there are infinitely many pairs of twin primes. That is, pairs of successive odd integers p and p plus 2 that are both primes. So electronic computers have discovered 152,891 pairs of twin primes, less than 13,020 pairs between 10 to the power of 12 and 10 to the power of 12 plus 10,000, which hints at their growing scarcity as the positive integers increase in magnitude. Many examples of immense twins are known. The largest twins to date, each is about 100,355 digits long. Imagine that certain number would be a very massive and big. So it is noted as, how many is this? 65516468355 times 2 to the power of 6 successive 3 positive negative 1. So it is about 65,569,468,355.2 plus positive negative 1. It is discovered way back in 2009. Consecutive primes not only can be close together, but also can be far apart. So that is, arbitrarily large gaps can occur between consecutive prime numbers. Stated precisely, given any positive integer n, there exist n consecutive integers, so all of which are in composite. To prove this, we simply need to consider the integers. N plus 1 factorial plus 2, n plus 1 factorial plus 3, as we come up to n plus 1 factorial plus n plus 1. So, where n plus 1 factorial is equals to n plus 1 times n times n plus 1 factorial, where we can have it 3 times 2 times 1. Clearly, there are n integers listed and they are consecutive. What is important is that each integer is composite. Indeed, n plus 1 factorial plus 2 is divisible by 2, n plus 1 factorial plus 3 is divisible by 3, and so on. For instance, if a sequence of 4 consecutive composite integers is desired, then the previous argument produces 122, 123, 124, and 125. So we have here 5 factorial plus 2 is equals to 122. It is equals to 2 times 61, which is both a prime number, right? So here we have the factorial of 5 plus 2. 122 is equals to 2 times 61. As we can see here, that 2 and 61 has even greater gaps. So the sum of the product of two prime numbers is an even number. We also have here 5 factorial plus 3 is equals to 123 is equals to 3 times 41. Obviously, both are still, what do you call this? Prime numbers. And we have also here 5 plus factorial plus 4 is equals to 4 times 31, and 5 factorial plus 5 is equals to 125 is equals to 5.25. Lemma. The product product of two or more integers of the form 4n plus 1 is of the same form. Proof: it is sufficient to consider the product of just two integers. So let us take k is equals to 4n plus 1 and k prime is equals to 4m plus 1. Multiplying those together, we obtain k of k prime is equals to 4n plus 1 times 4m plus 1. That is equals to 16m as we distribute, do the FOIL method. 16m plus 4n plus 4m plus 1 is equals to 4m n plus n plus m plus 1. So which is of the desired form? Theorem 3.6, so that will be discussed by another reporter. That could be all for my report. Thank you, everyone.
So next, we have the Theorem 3.6, which states that there are an infinite number of prime numbers of the form 4n plus 3. So we can prove this theorem by using the proof of contradiction. So in anticipation of a contradiction, let us assume that there exists only finitely many primes of the form 4n plus 3. We call them q sub 1, q sub 2, up to cube sub s. Consider the positive integer n is equal to 4 times q sub 1 times q sub 2 times until q sub s minus 1, which is equal to 4 times the quantity q sub 1, q sub 2, up to q sub s minus 1 plus 3. So here, notice that n is odd, so its prime factorization be exclusively made by odd numbers. But 2 is not part of this. Its prime factorization is made up of primes of the form 4n plus 1 and 4n plus 3. Now, what we are gonna claim is at least one of these primes is in the form 4n plus 3. So, to prove this, we are to do it by proof of contradiction, as what I have said earlier. So, let's suppose that all of its prime are in the form 4n plus 1. But if we take 4n plus 1 times 4m plus 1, it is equal to 4 times the quantity 4nm plus n plus m times plus 1. So, in other words, in the form 4n plus 1, it is close under multiplication. So that means we can never get numbers in the form 4n plus 3 when we use the form 4n plus 1, which means it is a contradiction of the original claim, which is that at least one of these primes is in the form 4n plus 3. So, thus, it is true that Theorem 3.6, there are an infinite number of primes of the form 4n plus 3. So next, we have the Theorem 3.7, which is the Dirichlet, which states that if a and b are relatively prime positive integers, then the arithmetic progression, which is a plus b, a plus 2b, a plus 3b, and so on, contains infinitely many primes. So it is also called an arithmetic progression. And then in Dirichlet's theorem, it states that this sequence contains infinitely many prime numbers. So the theorem is named after Peter Gustav Lejeune Dirichlet, extends Euclid's theorem that there are infinitely many prime numbers. Stronger forms of Dirichlet's theorem states that for any such arithmetic progression, the sum of the reciprocals of the prime numbers in the progression diverges, and that different such arithmetic progressions with the same modulus have approximately the same proportions of primes. Equivalently, the primes are evenly distributed asymptotically among the congruence classes modulo D containing A's co-prime to D. So, we have, if we put n sub k, which is equal to n plus kp for k, which is equal to 1, 2, 3, and so on, then the n sub kth term in the progression is what we can see in the presentation. Since each term on the right-hand side is divisible by p, so is a plus n to n sub kb In other words, the progression must contain infinitely many composite numbers. So the longest progression found to date is composed of the 23 primes, which we can see in the presentation, where n is greater than or equal to 0 and less than or equal to 22. So the prime factorization of the common difference between the terms is 2 squared times 3 times 5 times 7 times 11 times 13 times 17 times 19 times 23 and times 99839. So these are obviously prime numbers, so which is divisible by 9699690, the product of the primes less than 23. So this takes place according to Theorem 3.8, which will be discussed by Nicel Salise. Thank you.
Theorem 3.8. If all the n is greater than two terms of the arithmetic progression p plus d, p plus 2d up to p plus n minus 1 times d are prime numbers, then the common difference is divisible by every prime q is less than n. For the proof, consider a prime number q is less than n and assume to the contrary that q is not divisible by d. We claim that the first q terms of the progression p plus d, p plus 2d up to p plus q minus 1 times d will leave different remainders when divided by q. Otherwise, there exist integers g and k with g is greater than or equal to 0 and z is less than k and k is less than or equal to q minus 1, such that the numbers p plus gd and p plus kd yield the same remainder upon division by q. Then q divides the difference k minus g times the d, but GCD q and d is equals to 1. And so, Euclid's lemma leads to q divide k minus g, which is nonsense in light of the inequality of k minus g is less than or equal to q minus 1, because the q different remainders produced from equation number 1 are drawn from the q integers 0, 1 up to q minus 1. One of these remainders must be 0. This means that q over p plus td for some t satisfying t is greater than or equal to 0, but less than or equal to q minus 1. Because of the inequality, q is less than n is less than or equal to p is less than or equal to p plus t times the d, we are forced to conclude that p plus t times the d is composite. So if p were less than n, one of the terms of the progressions would be p plus pd equals to p times the quantity of 1 plus d. With this contradiction, the proof that q over d is complete. It has been conjectured that there exist arithmetic progressions of finite but otherwise arbitrary length, composed of consecutive prime numbers. Examples of such progressions consisting of 3 and 4 primes respectively are 47, 53, 59, and 251, 257, 263, and 269. It has been shown that no polynomial of the form n squared plus n plus q with q a prime can do better than Euler polynomial in giving primes for successive values of n, and that until fairly recently, no other quadratic polynomial of any kind was known to produce more than 40 successive prime values. The polynomial function of n is equals to 103n squared minus 3945n plus 34,381. Found in 1988 produces 43 distinct primes values for n is equals to 0, 1, 2, and up to 42. The current record holder in this regard for the function of n is equals to 36n squared minus 810n plus 2,753, thus slightly better by giving a string of 45 prime values. The failure of the previous functions to be prime producing is no accident, for it is easy to prove that there is no non-constant polynomial for the function of n with integral coefficients that takes unjust prime values for integral n is greater than or equal to 0. We assume that such a polynomial function of n actually does exist and argue until a contradiction is reached. So, let this function showed in the PowerPoint, where all the coefficients a sub 0, a sub 1 up to a sub k are integers, and a sub k is not equal to 0. for a fixed value of n sub 0, p is equals to function of n sub 0 is a prime number. Now, for any integer t, we consider the following expression. The expression is displayed here at the PowerPoint. So where q of t is a polynomial in t having integral coefficients. Our reasoning shows that p is divisible by f function of n sub 0 plus t times p. Hence, from our own assumption that the function of n takes only prime values. So the function of n sub 0 plus t times p is equal to p for any integer t, because a polynomial of degree k cannot assume the same value more than k times. We have obtained the required contradiction. Okay, for example, the sequence 5, 11, 17, 23, and 29. So, the sequence is an arithmetic progression with our common difference of 6, and our n here is 5. Now, let's check if all the terms in the progressions are prime numbers. So, 5 is a prime number, 11 is a prime number, 17 is also a prime number, 23 is a prime number, as well as 29 is a prime number. So, based on this analysis, we can see that all the terms in the sequence are prime numbers. However, we also need to verify if the common difference, which is 6, is divisible by every prime q less than n. So in this case, the primes less than 5, the last term which is the last term in the sequence, are 2 and 3. So the common difference 6 is divisible by both 2 and 3. Therefore, the sequence 5, 11, 17, 23, and 29 satisfies the conditions of the Goldbach Conjecture Theorem 3.8. That would be all. Thank you and God bless.